In this section of valuation basics, we're going to be valuing a perpetual bond. If you remember from the previous section, a term bond was a bond that paid coupon payments over a given term, and at the end of the term, the face value was remitted to the bondholder. In this case, what we're going to do is we're going to assume that rather than having a fixed term, that this bond goes into perpetuity. So in other words, it pays coupon payments, but it never pays the principal back. And we'll also assume that this bond can grow over time. You can look at the U.S. Federal debt of approximately 40 trillion as a perpetual bond. Really, what you have is you have the Treasury who started to issue short-term paper that rolls over, every 3 months, every year, what have you. But it rolls over, and then in order to refinance, the Treasury actually borrows a certain percentage more than the bond face that matured. So really, you can look at the U.S. Fiscal position as far as its debt as being a perpetual bond. Our hypothetical problem will be pretty much the same as in the previous section on term bonds, except that right now, or for this exercise, we're going to be valuing a perpetual bond given the following parameters. The bond face value is still 100,000. It still makes one annual payment, coupon payment, but there is no term. It just makes a coupon payment forever. The coupon payment for this exercise will be 5.75%, and then we're going to allow the principal to grow. So what you will have is you will have a bond, a perpetual bond, where the principal value grows and grows and grows. So the coupon payment itself grows and grows and grows, but the principal is never repaid. We'll assume a real rate of return similar to or exactly the same as in the previous section of 2.25%. The annual inflation rate of 2.75%, and the annual risk premium, which covers default risk, term risk, and all that kind of stuff, is 1.7%. In this slide, we're going to take a look at some model parameter calculations. E1 is the value of the perpetual bond at time zero. And if we go back to the value of the term bond, the value of the term bond was the value of the coupon payments plus the value of the principal payment. But in this case, the principal is never going to be repaid, and there's no term. So therefore, the value of the perpetual bond is going to be the value of the coupon payments. But in this case, we subtract out the value of the principal received by the bond issuer. Because what happens is that from the standpoint of the bondholder, assuming this was one big perpetual debt blob, um, the debt holder or the bondholder would receive the coupon payment, but it would also remit to the bond issuer the increase in the principal. And remember that the principal increases and increases, so the coupon increases and increases. So therefore, the value of this perpetual bond is the value of the coupon payments minus the value of that check that the bondholder has to cut to the issuer to increase the principal value of this perpetual debt. Equation E2 looks at the value of the principal. This is actually it's not a value. It's just the principal balance or the face value. Remember, it's going to grow, and here we're going to say it's going to grow at a rate of G, and G in our case is 3.5%. So therefore, the face value has to have a subscript T, which means it's time dependent. So according to equation E2, the face value of the bond at time one, at the end of year one, would be the face value at the end of year zero, or now, times 1 plus G to the 1 power. So the face value will increase over time, and E2 is the equation for that face value at any point in time. E3, just like in the case of E2, E3, the coupon payment is not a fixed amount. It will grow over time. So we define the coupon payment as capital C, but in this case we add a subscript T, because the coupon payment is time dependent. So the calculation there would be is the coupon payment at the end of year T would be the bond principal at the beginning of that time period times the coupon rate. So therefore, we're going to say that the coupon rate is R, small r. So you can see that in that equation at the very end that the coupon payment would be R, which is the coupon rate, times the principal value at the beginning of the year. So that would be the coupon payment. Now, the E4 is the principal received, the value or the principal received by the bond issuer at any time t. And again, we're going to say that's P, and P is time dependent, so we're going to add a subscript T. So therefore, the bond principal received, or this is the check that the bond holder has to cut to the issuer at the end of every year, is going to be the bond principal balance at the beginning of the year times the principal growth rate, which is in this case is G. So if we took equation E2, then the bond principal, the check that the bondholders have to cut to the issuer would be G times that face value at the beginning of the year. Equation E5 is the market rate of interest, small k. This is the same as in the previous slide. So the market interest rate would be the real rate of return plus the inflation rate plus the risk premium. And if we go to our bond parameters, the rate or the market rate of interest would be 6.7%. And again, we can make the intuitive guess or a statement that because the bond coupon rate of 5.75 is less than the market rate of interest, which is 6.7%, then this bond, just like in the case of a term bond, should sell at a discount. So to price our bond, we want to take a look at some bond value equations. And if we look at E6, this is the value of the perpetual bond. Note that our cash flow at any period of time is the coupon minus the check we have to cut to the issuer. So that's C minus P. And because both the coupon payment and the check we have to cut to the issuer increases over time, then we have to subscript that. So the first so if you look at E6, the value of the perpetual bond equals that first cash flow, which is C1 minus P subscript 1. We divide that by 1 plus K to the 1 power. Same thing with period 2 or year 2. It's the coupon payment we receive at the end of the year 2 minus the check that we have to cut the issuer at the end of year 2. We divide that by 1 plus K to the 2, and we go all the way out into infinity. So therefore, we want to condense, because obviously we don't want to have an equation with infinite cash flow. We want to represent that in something that we can use. And that's what we're doing in equation E7. Just like in the case of the term bond, what we did is we took all those cash flows and we used a summation, the Greek letter sigma, where the subscript to t equals 1. So we start at year 0. And then the superscript you can see is infinity, which means that this goes from time 1 to infinity. And then we discount all those cash flows for each one of those years. So at the end of that equation, you can see that our equation for bond value becomes V subscript 0 equals R minus G over 1 plus G, R minus G over 1 plus G times principal at the beginning of the year, beginning of the year 0 times that summation. What we want to do now is we want to use a discount factor just like we did for term bonds. So we want to define that discount factor as 1 plus G over 1 plus K. Remember that for the term bond, the discount factor was 1 over 1 plus K. But for the perpetual bond, because it's growing at the rate of G, the discount factor becomes 1 plus G over 1 plus K. So what we've done is we've used theta. We went to equation E7 and we replaced all of the 1 plus Ks and the 1 plus Gs with that theta value. So the equation at the end of the day becomes much, much simpler. Equation E8 basically says is that the value of the perpetual debt equals R minus G over 1 plus G times the principal balance at the beginning of year 0 times that summation. And just like with a term bond, that summation is a geometric series. So the last thing that we want to do is go through that summation and manually work through it, because we would have to take theta to the 1 plus theta to the 2 plus theta to the 3 all the way to theta to the infinity, and by definition we would never get there. What we want to do is we want to express that summation as a geometric series and try to get a closed form solution for that, which is what we do. What we do is we note the geometric series in the term bond was theta minus theta to the t plus 1. But in this case, capital T would be the term, which is infinite. So therefore, the geometric series becomes theta minus theta to the infinity plus 1 over 1 minus theta. So you can see that theta to the theta minus 1 is, or the theta plus 1 goes to 0. Because any fraction that between 0 and 1, which our discount factor is, if we take that to the infinite power, it goes to 0. So therefore, we can eliminate that altogether. So our geometric series, the solution to that geometric series becomes theta over 1 minus theta, which makes it pretty simple to use. So what we want to do is we want to say, okay, we had equation E8, which had that summation, and then E9, which had the solution to that summation, and we want to combine those two. So if we do that, we get E10, and we basically say that the value of our perpetual bond is going to be R minus G, which is the coupon rate minus the growth rate, times the principal balance at the beginning of year 0, over times 1 over K minus G. And that's the value of our perpetual bond. What we want to do now is look at the discount factor over time, just like we did with the term bond. So if we go to E8 there, equation E8 at the bottom of the slide, we define the discount factor theta equals 1 plus G over 1 plus K. And then we go in and we look at the parameters to our problem. And G is the growth rate of principal, which is 3.5%. And K is a market rate of interest, which is 6.7%. So if we put those values in for G and K, then we get a discount factor equals 0.97001. So again, the question becomes, if we take a look at that table to the left-hand side, we have the years going from 0 to 10. And remember, with a perpetual bond, it actually goes from 0 to infinity. Well, obviously, we can't chart out infinity. But the same thing with the term bond. Year 0, the discount factor is 1. Basically, that says is if I'm currently standing at year 0 or at time 0 and get $1, what's that dollar worth? Well, it's worth $1. Same thing with year 1. If I get $1 at the end of year 1, what would I pay for that dollar today? And it's approximately 97 cents. And we go all the way down. And if we take a look at that graph to the right-hand side, this is a discount factor over time. We start at year 0 where the discount factor is 1, and then as we go through time, the discount factor gets less and less. And if you take that graph and rather than going from 0 to 10 years, if you go 0 to 1,000 years, what you're going to find is that the discount factor goes to 0. So now that we have our equation for perpetual bond value, we can solve our hypothetical problem. And if you go back to the beginning of the slide series, you'll see that if you look at that table, B subscript 0 is the bond principal at time 0, which is 100,000. The symbol R is the bond coupon rate, which is 5.75%. G is the bond principal growth rate, which is 3.5%. And K is the market rate. This is what the market expects on this perpetual bond, and that's 6.7%. So now that we have our equation and all of our parameters, we can actually solve for the value. So what we're going to do is we're going to take equation E10 and split that up into two pieces. Notice that E10 starts with R minus G, so we're going to evaluate the R part first, which is the value of the coupon payments. And then we're going to subtract out the G part, which is the value of the principal payments that we make to the bond issuer. So E12A, that's the value of the coupon payments. And what we do is we take R, which is the coupon rate, times B subscript 0, which is bond principal at the time at the beginning of year 0, times the fraction 1 over K minus G. And so that's what we do there using the parameters in the table above. So what we have is we have 5.75 0.0575, which is the coupon rate, times $100,000, which is the principal balance, times 1 over 6.7%, which is the market rate, minus the growth rate of 3.5%. So the value of those coupon payments is $179,687.50. So if we go down to equation E12B, that's the value of the principal payments. Basically that's the value of all the checks we have to write to the issuer. Because in compensation for having increased coupon payments, we have to cut the issuer a check, obviously. So the value of the principal payments is G times G, which is the growth rate, times our principal at the beginning of year 0, times a fraction 1 over K minus G. And so if we take our parameters of the problem and substitute them into that equation, what we have is we have 3.5%, which is a coupon or the growth rate, times 100,000, which is the principal, times 1 over 6.7% minus 3.5%. So the value of all those principal payment checks that we have to write to the issuer is 109,375. So E14 or at E12C, that's the bond market price. So we take E12A minus the E12B, because remember that the benefit of owning this perpetual bond is we get coupon payments worth 179,000. But the disadvantage of having this perpetual bond is we have to constantly make principal remittances to the bond issuer, and so the value there is 109,000. So our bond market price is therefore 179,687.50 minus 109,375. So therefore the value of our perpetual bond for our hypothetical problem is 70,312 and 50 cents.